All right, in this video, we're going to talk about this term net force. So we see the term net force in the momentum principle equation, which is F net is equal to the derivative of momentum with respect to time. This is also the same thing as Newton's second law, which is often stated as F net equals ma. So we're going to talk about what we mean by F net. Sometimes people confuse F net with just F, like a force gives us this, but it's really the sum total of all forces, which is what net force means, is what's going to give us the rate of change of momentum or mass times acceleration. So we have to add up all of the forces in order for this equation to work. The tricky thing here is that force is a vector. So we have to add the forces by adding their components. We can't just add the forces, the magnitudes of the forces. We actually have to know their components or their directions or something like that in order to add them properly as vectors. So let's look at an example. Let's say we have two forces, force 1 and force 2, with their components shown here. So force 1 has 12 newtons of force in the x direction and negative 36 newtons of force in the y direction and 0 units of force in the z direction. And then for F2, we've got negative 15 in x and positive 36 in y and 0 in z. All right, so in order to add these forces, we actually have to add their components together. So we add the two x components, we add the two y components, and we add the two z components. And when we do this, we see that our sum total is negative 3 newtons x, 0 newtons y, and 0 newtons z. All right, so that's an example where we're given straight up the components of the vector. Now let's look at a different example. So in this example, let's say that we're given three forces, and instead of given their components right away, we're actually just given that force 1 is 30 newtons up, force 2 is 10 newtons right, and force 3 is 15 newtons down. Now, most people, what they want to do here is they just want to take those three numbers and add them up. That would be adding the forces, right? Well, no, we can't do that because these are not scalars, they are vectors, so their directions matter. So we cannot just take the magnitudes and add them up. What we want to do is we want to add these things like they are vectors. So the first step is often to draw this out if you can, especially if it's a two-dimensional thing. It's nice to draw it out to visualize it and see it. So here I've drawn force 1 and it's 30 newtons up. So I have an arrow pointing up with a certain length. We'll call that length 30 newtons. All right. Force 2 is 10 newtons to the right. So it's a shorter arrow. It's only about a third of the length of force 1 and it's to the right. And force 3 is down 15 newtons. So it's about half the length of that force 1 that we saw. So when we add up the forces and we look at their sum actually goes up and to the right. It's not, the direction matters, right? So it's not purely up, purely right, or purely down, but a combination of these directions that we started with over here to get us a total force vector, a net force vector that is up and to the right. Okay, when we add forces like this is something I like to call a force vector addition diagram. And this will come in really handy later when we are dealing with forces as well. Okay, so the net force in this case, we could just take the x components, the y components, and the z components and add them up. And in this particular situation where in this particular example, we just have one component in the x direction, or one force that's in the x direction, and it's purely in the x direction. It has no y or z components, and that's force 2. So I'm going to put that in my x component for my net force. The y component, though, we've got two forces in the y direction. That is F1 going up and F3 going down. So I have 30 newtons, positive 30 newtons and a negative 15 newtons for my y. And I have 0 components of force from any of these three forces in the z direction. So this, if I add these all up, this is then the total net force. We could do 10 newtons x, 15 newtons y, and 0 newtons z. So that is an example here where we've got, we found the components and we added them up with the components. But first, we were given just words, right? we're just given words here. And we drew out a diagram to kind of see that net force and what it looked like. And now we can see our final net force is got an x component. So this is to the right and this is up. And that's what our final force vector looks like on that diagram. Okay, but what if we wanted to have our final answer not in component form like this, but we actually wanted to know exactly what the magnitude and direction was of the net force? So to do this, first we're going to start off with magnitude, and we add the components in quadrature. So we're going to add the x component squared plus the y component squared plus the z component squared. I didn't put that in because it's just 0. Take the square root, and we get 18 newtons. So it's approximately 18 newtons is the net force. And then we want to figure out what this angle is here of the net force. And to do that, I'm going to use the inverse tangent of the y component over the x component. And that gets me about 56.3 degrees. So the net force here, we could say, is 18 newtons, 56.3 degrees above the right horizontal. So notice, because force is a magnitude, or a vector, it has both a magnitude and a direction associated with it. So my final answer has either got to be the component form or the form where I'm writing out both the magnitude and the direction.